One of the first things that you're going to learn about in any chemistry course is how to work with units of measurement. Why? Well, because they're incredibly important, and also because we are going to be using them throughout the course. And primarily, we're going to be working in something called the metric system. The metric system is quite similar to the SI system. They have subtle differences, but we're not going to worry too much about that right now. We're going to focus our attention instead on the fact that units can be used to measure things like length or volume, mass, temperature, time, all of the things that you would expect. The metric system is used in most of the world and absolutely everywhere by scientists. So let's take a look at the units that are used to define the metric system and the system international. First thing we're going to consider is length. Well, in the metric system, the standard way that we measure length is in the meter. Same is true for the system international. For volume in the metric system, the standard unit is the liter. And in the SI system, it's the cubic meter. So you see this is where the subtle variations come in. For mass, metric system is gram. For SI system, it's kilogram. For temperature, we have Celsius in the metric system and Kelvin in the SI system. So these are some of the things that we need to wrap our mind around. What is the metric system? What is the system international? And you might even find yourself feeling a little curious about how did this get developed? Has it always been around? The answer is no, it hasn't always been around. It's a very orderly and organized system that really had its birth in the late 18th century. In fact, around the time of the French Revolution, where people, scientists in particular, were looking for a more uniform way to define and deploy units. I skipped one here. The final one measurement we should consider for now is time, both second for metric and system international. Now, if you're curious, you might be asking yourself, well, how do we know, like, who decided what a gram is? How do we know what a meter is? Is there some kind of reference that we need to define what a meter is? And the answer to that is absolutely yes. So let's just take a look at how the meter is actually defined, because I think it's going to surprise you. The meter, scientifically, is defined as the length of the path traveled by light in a vacuum in about 1/300 millionth of a second. We know meter is a measure of length or distance, right? So this kind of makes sense. But who knew until we looked it up in Wikipedia? And I encourage you to be curious about this kind of stuff. Maybe you're curious to know how a gram is defined. Well, go look it up. Go look in Wikipedia. See what it has to say. A little plug for the metric system. We don't use it in the United States commonly, but the fact of the matter is pretty much everyone uses it. The United States, as you see here in red, a little bit of an outlier. Wouldn't be the first time the United States was an outlier, but really the whole world is using the metric system. So we should too. And we're going to learn all about the various units beyond what we just looked at. And we're going to dive even deeper into metric units. And you're going to have to learn and memorize them. We're going to start with the idea of metric units and prefixes. So what is a prefix? Well, a prefix is something we put in front of a unit. So we just said a minute ago that the metric system uses the liter as a measure of volume. So if we take the liter and we put a deci in front of it, by definition, we have changed the size of the liter. In fact, if we say deciliter, the liter has suddenly become 1/10 of a liter, or as you see here, 0.1 of a liter, or 10 to the negative 1 of a liter, because 10 to the negative 1 by definition is 1/10 of a liter. Now notice all of these prefixes that we're looking at here, centi, milli, micro, nano, pico, and femto, all make the reference unit smaller. It could be a liter, it could be a meter, it could be a gram, it could be a second. Doesn't really matter. When we put centi, as you see in this second example, in front of a meter, suddenly we have 0.01 of a meter. Another way of looking at that is 10 to the negative 2 meters, or 1/100th of a meter. Milli, I think you're starting to get the idea here, would be 0.001 seconds, or 1/1000th of a second. Micro, 1/1,000,000th of a second. So guess what? I could read all these to you, but now would be the time to pause the video and just look at these, study them, think about them, and try to understand them. Notice as we go down the line here, the effect of putting one of these prefixes in front of a unit makes them smaller and smaller and smaller. By the time we've gotten to femto, a femtosecond is 10 to the negative 15 seconds. That's really almost unimaginably small. So you're going to have to memorize these. You will be tested on these. You will be tested on them extensively in ALEK's homework, and you will be expected to know them. So sometimes in chemistry, you have to memorize. This is one of those times. Okay. I want to point out something to you now that can be quite confusing when you're first trying to learn about this. If you want to say 1 meter equals how many centimeters, that is a very different thing from saying you have 1 centimeter and how many meters is that. So let's think about it. A centimeter, by definition, is a much smaller unit than the meter. So actually, 1 meter equals 10 to the 2, or 100 centimeters. However, if we want to express centimeters in terms of meters, we have to flip this on its head. 1 centimeter, small, is actually equal to 10 to the negative 2 meters. So you have to develop a facility with knowing when you're going from meters to centimeters, trying to take a meter and expressing it in terms of centimeters, you need 100 of them. But on the flip side, if you're taking a centimeter and you're trying to turn that into a way you can express it in meters, you have to say that a centimeter equals 1/100th, or 10 to the negative 2 meters. Read through these bullet points here. Think about it and try to practice going back and forth between these two different and yet similar conversions. Now, we're just looking here at prefixes, as I said, that decrease the size of the unit. They have the effect of taking the base unit and creating a smaller unit. What if we were looking at the opposite situation? So we have prefixes that have the opposite effect, prefixes that are larger units and that increase the size of the unit. So once again, we have some kind of reference unit. So if we're looking at peta, the first one on the list here, notice that we're going to use as our base unit, we're going to use the gram. So peta actually represents 10 to the 15 grams. 1 petagram equals 10 to the 15 grams. 10 to the 15. Think about that. The 15, it's a very large exponent. So a petagram is a very huge unit. We've put a lot of zeros. We've added a lot of zeros onto our unit, right? Once again, we go on down the line here. Tera, giga, mega, kilo. Now, the ones that we're going to be working with the most in this course are these three. So 1 gigameter, for example, equals 10 to the 9 meters. 1 megagram equals 10 to the 6 grams. And 1 kilometer equals 10 to the 3rd meters. Again, you must memorize all this stuff. I know it seems a little painful, but once you get it under your belt, not so bad. So which ones, when I say memorize, must you really, really, really know by heart? Well, guess what? I have done you a favor here, and I'm telling you that you really must know these. These are the ones that you're most likely to get tested on. And I'm going to remind you one more time about this kind of back and forth thing that I just mentioned, which is highlighted here. 1 millimeter equals 10 to the negative 3rd meters. However, 1 meter equals 10 to the 3rd millimeters. Think about it. Get this one into your head and don't let yourself get bollocksed up, because I'll tell you what a common mistake is, and a mistake that you want to avoid, and I see all the time. 1 millimeter equals 10 to the 3rd meters. This makes absolutely no sense. A millimeter is a tiny unit. It can't possibly equal 10 to the 3rd meters. So think about it when you try to set up these relationships. You don't want to make this kind of mistake. You also, I could give you one more example of a mistake you could make. You could also say 1 meter equals 10 to the negative 3rd millimeters. Equally bad, to be avoided. What we've been talking about all along here, really, is something called an equality. We can say, as we just pointed out, that 1 meter equals 10 to the 3rd millimeters. Now, we have an equal sign here. We know that if we measure 1 meter, it's the same thing as saying we have 10 to the 3rd millimeters. So we're very concerned with these equalities in chemistry because we're going to use them subsequently to convert between one kind of unit and another kind of unit. So what are the kind of conversions that we're going to be doing? Well, all kinds. In fact, you're going to convert in chemistry. You're going to be doing a lot of this, so you want to get really good at it. And in order to get good at it, you have to be able to use equalities, and you also need to know how to turn them into conversion factors, which we're going to talk about in a minute. Okay, so we just talked about the metric system, and we talked about all these different ways that we might want to measure things. So here are a bunch of conversion factors. I don't think I really need to go over these. You can look at them yourself. There also, however, sometimes we might want to convert within the US system, in which case, what are the kind of things we would need to know? Well, if we wanted to convert some measurement in feet to some measurement in inches, we would have to know that 1 foot equals 12 inches. Now, the good news is you don't have to memorize US. No memorization. I would generally provide you with these equalities if you need them. As noted, yes, memorize here. And also, you don't have to memorize metric to US. I won't ask you to do that. These equalities would be provided. Metric is your main focus. Okay. But we can use any equality. The main point is we can use any of these qualities. If we want to convert from miles to feet, well, we need to know how many feet there are in a mile. If we want to convert, I'm just going to pick something randomly here, from kilometers to miles, well, we need to know there's 0.621 miles in a kilometer. That hopefully is pretty obvious. You're never going to get from A to B if you don't know what is equivalent to what. So how can we actually convert? Well, in order to convert effectively in chemistry, you're going to want to be able to use a plan. Always good to have a plan. Whether for life or chemistry, you want a plan. So I'm going to give you this guide, which you could, should, must follow when you are trying to make a conversion. So step 1, state the given and needed quantities. Once again, I'm going to randomly pick something. You have 10 meters, and you want to know what that is in centimeters. So this is your given, and you want to figure out your needed centimeters. Now you want to write a plan to convert the given unit to the needed unit. And quite frankly, this plan is going to involve stating the equalities and the conversion factors. So a plan could be a simple sketch like, I just want to go from 10 meters to question mark centimeters. And for that, I need to know that 1 meter equals 10 to the 2 centimeters. That's my equality. And then I'm going to set up the problem so that units cancel and I can calculate the answer. And that's going to look something like this. 10 meters times 10 to the 2 centimeters per 1 meter. Look what's going to happen here. Meters are going to cancel, and I'm going to get an answer of 10 to the 3rd centimeters. So this is a very simple example of how you could deploy this conversion plan in order to get the right answer. So let's look a little bit more deeply at the mechanics of this process. Determine which unit conversion factors are needed. Okay, we talked about that just now. And we can always say the given quantity times the conversion factor will equal desired quantity. So notice if we go back here, I said 1 meter equals 10 to the 2 centimeters. Here, I actually turned it into a conversion factor. How did I do that? Well, I set it up as a ratio. If 1 meter equals 10 to the 2 centimeters, then there is a ratio of 10 to the 2 centimeters for every 1 meter. This is what makes an equality a conversion factor. So now let's think about how if we take our given unit and we multiply by the desired unit over the given unit using our equality, the given unit will always cancel out and give us our desired unit. That's what I just did right here, converting 10 meters to centimeters. Where did things cancel out here? Meters canceled out because my given unit, meters, was set up in such a way that I would only be left with my desired unit, which is centimeters. If all the units cancel except for the desired units, in other words, if you have set this problem up in the right way, the problem will be solved correctly. You can take that to the bank. Okay, now my favorite example to give my students, seeing as how I have a cute but somewhat fat beagle, is to talk about how I would convert my beagle's weight in pounds to, let's say, kilograms. Okay, so let's say my beagle weighs 45 pounds, which is a lot for a beagle, but he does weigh around 45 pounds. So what is this? This is my given. And I want to know what he weighs in kilograms. So this is my needed. Now, what equality do I need? Well, I need to know the relationship between pounds and kilograms. And I happen to know, off the top of my head, fortunately, that 1 kilogram equals 2.2 pounds. So this is my equality. How can I set this up as a conversion factor? Well, clearly I could do it one of two ways. I could say 1 kilogram over 2.2 pounds. But I could also say 2.2 pounds over 1 kilogram. So I'm going to have to ask myself when I'm setting up my conversion problem, which one of these is correct. So as illustrated in this banner up here, I'm going to write down my given unit first, which is 45 pounds. And now I'm going to have to decide which one of these am I going to use. And it has to be the one that's going to cancel out correctly. So the fact of the matter is, in order for me to end up with my desired unit, which is kilograms, I'm going to have to use this one. 1 kilogram over 2.2 pounds. Okay, so when I multiply this out, are my units going to cancel correctly? I have a good feeling about this. It looks to me, definitely, when I multiply these across, that the numerator and the denominator will cancel out. Now I'm going to take 45, I'm going to divide it by 45, I'm going to divide it by 2.2, and I'm going to get the answer of, I haven't really gotten into significant figures yet, so I'm just going to say, I'm going to cheat a little. I'm going to say 20.5 kilograms is the weight of my beagle. So I have converted successfully from pounds to kilograms. And it really wasn't too painful. Now let's have a little bit of fun with Serena Williams, a really amazing tennis player, as you probably already know. Her fastest serve recorded is 126 miles per hour. And I forget what year that was. You can look it up on Wikipedia. But I would point out, ladies, that it was a mile per hour faster than the fastest men's serve, Novak Djokovic. He was faster than the Joker. So 126 miles per hour, fastest serve. But let's say I like to just sometimes dream up my own problems. I have dreamed this one up before, and it's a favorite, so I keep using it, but I encourage you to kind of like experiment. Come up with your own problems and see if you can solve them. Anyway, let's say hypothetically we want to know how fast this serve goes, not in miles per hour, but in meters per hour. So, as always, we need an equality that we turn into a conversion factor. And 1 mile, it just so happens, equals 1.6 meters. So we're going to do the usual thing. We're going to say 126 miles per hour, and we're going to set this up so that miles cancel and we're left with meters. 1.6 meter per mile. Miles cancel. What's 126? Somebody help me. 126 times 1.6 equals 201.6 meters per hour. Okay, well, that's kind of cool, but that was maybe even just too simple. What if I really wanted to go and say, how fast does her serve travel? How many meters does her serve travel in a single second? Well, we now have 201.6 meters per hour, and we need to convert hours to seconds. How many seconds are there in an hour? Well, if there are 60 minutes in 1 hour and 60 seconds in 1 minute, that means we have 3,600 seconds in 1 hour. So we can use this. But how are we going to use it? We have to set up our conversion factor. We have to multiply across, I should say, so that hours cancel and seconds are left behind. Notice hours are now in the denominator, so we're going to have to put the hour on top and the 3,600 seconds on the bottom. Okay, back to my trusty calculator, which is not showing up on my phone here. Very naughty. Okay, so 201.6 divided by 3,600. That means 0.056 meters per second. That's how many meters her serve goes in a second. I'm still not happy with that. Now I want to know how many centimeters it goes in a second. You can see we could go on with this forever. 0.056 meters per second times what? 10 to the 2 centimeters per meter. Okay, you know what? I was bad up here. I didn't cancel out my units. Okay, so now meters are going to cancel. We're going to move this 2 decimal points over, and we're going to say Serena Williams' serve travels 5.6 centimeters in a second. Now the truth is, if you wanted to have gone, hypothetically, from miles per hour to centimeters per second, you could have set this up all in one step. Isn't that amazing? But that's a little advanced for right now. We're going to get to that. We're going to break it down first, and then we're going to bring it all together later. But as I do encourage you to kind of like be creative, make up your own problems, and get to know your units and your conversion factors.